Hello, everybody. My name's Albert Meyer. For those who don't know me, um, and today I'll be sharing with you my midterm presentation. This lecture is going to be on relativity in orbital mechanics. So let's just get into it. So this is the outline of the lecture. Just gonna share a brief introduction, go through some background on relativity, go through a historical case, which is Mercury's orbit, how do we apply it, and then wrap up. So, our motivation. What we have here is why do we care? Well, Newton's laws are really good for most orbits, but as you know, we have plenty of perturbations, as can be seen on the right here in this graphic that we have went through quite a few times in class. And you can see relativity is on there. I have it boxed in over here. It is lower than most of the other perturbation effects, such as the J2 effect or tidal effects or anything like that, but it is still important because it is a measurable perturbation. And even though this measurable perturbation is really small, it will add up over the long term. And we'll see that relativity is very important for either very precise systems or systems that are going to have a long mission duration. And if we want to do some long-term orbital determination, we'll see how the relativity effect adds up and can really throw these orbits off in the long term. So, here's some background. I'm sure we've all seen Newtonian gravity before, but I think it'll be good to go through it just to show how relativity stacks up against it. So, 1687, Newton writes down his famous equations of motion, um, including this force term, which describes gravity as we know it. So, this gravity is implemented into Kepler's equations and observations to give us Keplerian orbits. Just some basic assumptions that we make when we're doing Newtonian gravity is that space and time are absolute, meaning that they don't vary from frame to frame. If I, say, am moving faster than you, even, near, say, just a few orders of magnitude faster than you, we'll see that relativity will play an effect on that. But in the Newtonian assumptions, that does not exist. We also assume that gravitational fields are central and they are also spherically symmetric. Now, this helps our two-body problem turn out very nice. It's a very well-behaved problem. And uh, we could see on the right here that we have our Kepler orbit in this dashed line, and this orbit is not precessing in time. It is very nice closed form solution, and it'll just keep going in this circle forever and ever. And this works well as an approximation for low speed orbits. And when I say low speed orbits, I know satellites are moving very fast, but we're going to say low speed relative to the speed of light. And for weak gravitational fields. And for the purposes of this lecture, we're going to say that Earth has a weak gravitational field. And this is true when you consider some stronger gravitational fields, such as those of our sun, other stars, or, near the extreme. There's also bodies that orbit black holes and stuff like that. So it can get pretty funky. So Newton works very well in most cases, but as you can see, we have the relativity prediction for this orbit here, and it kind of spirals off and does not stay along the original path that the Keplerian orbit does. So, first, Einstein writes down special relativity in 1905. Now, what this says is that space and time are not separate things, that they are actually related to each other. Um, so, if I he establishes the space-time framework, which we'll get more into in a second. Um, but is really the most important at high velocities and in very strong gravitational fields. So the big takeaways here is that there's or the big idea is that there's two postulates of special relativity. The first is that the laws of physics are identical in all inertial reference frames. So what this means is that in an inertial reference frame, no, you are not accelerating. Um, so if I am here on Earth and somebody is out in a satellite going at a constant velocity, the laws of physics should obey the same nature in both frames. So there is no preferred frame to do the math from. Either way, the laws of physics should behave the same and we should get the same answers. So the second is that the speed of light is a fixed finite value. It's about 3 times 10 to the 8 meters per second. And this speed is independent of the source of the light, and it is independent of the person observing the light. So what this really leads to is time dilation and length contraction. And we'll be talking about time dilation in a bit. Length contraction is not super relevant to our systems, even though it does play a small part, um, and a measurable part in systems like the ISS, where you'd see it's on the order of about uh, e to the negative 10. So, well, the key takeaways from these two is that time dilation, which will be important to us if we do care about satellites and other orbiting bodies, that it will mess with onboard clocks. And another thing is that just special relativity serves as the framework for general relativity, which we'll go into a second, which affects gravitational fields and has more of a direct effect on orbits. So, general relativity. 1915, 10 years after special relativity and over 200 years after Newton's laws. So it's pretty incredible that this uh, missing piece of the puzzle took so long to discover. But it extends special relativity to include acceleration and gravity. And you've seen the equations of motion, so you know that those are two things that we really care about. And it reinterprets gravity not so much as a force, but as curved space-time and objects moving through that curved space-time. So, if you look at this picture on the right, I think this is the best way to explain this because you really need a visualization. So, this uh, body in the middle is a massive object, and you can see that it is bending the space around it. If you look at where this star is, it looks like it's apparently along the dotted line. So, we know that it's not along this dotted line now, but uh, based on Newtonian theory alone, you would not be able to deduce where the actual position of the star is. Now, this star is actually behind this massive body, and the space is bending the light because this uh, line wants to be along a straight and shortest possible line in this bent space. So, as you can see, this star is actually located behind this massive body, and you would not think you should be able to see it, but that is just how this works, and it is a little funky. So, very cool. Um, and this is only the case because this is such a massive object. So, if this was not such a massive object, we would kind of get what Newton said in our laws. So the big takeaway from that is that general relativity breaks down into Newton's laws when there's either a weak gravitational field or the velocities aren't very high. Now, another thing to take away from this is that this is bending light, light which is massless, light that would not be bent under Newton's laws in this way. So, down here in the bottom left, I've included this abridged version of the Einstein field equation. Now, this is not a usable form of the equation. It is just me showing you uh, how this effect works. This G and T are both tensors, so you can't really apply this, but G is the curvature of space-time, T is the mass and energy of your object, and then K is this Einstein gravitational constant, which is on the order of 10 to the negative 43. So you could tell that the takeaway is that the effect is very, very small unless you have a lot of mass in a very massive object with a lot of energy. So you're not going to be bending space-time unless you are a supermassive object. So what does this mean? Now, these are some key equations that can be derived from general relativity. I will not be doing that in this lecture. I'll leave that to Dr. Fitzgerald. I believe that he will be giving a lecture on that at the end of the year. But nonetheless, I will show them to you here. So this is this first equation is the correction term for acceleration. So if you wanted a first order accurate correction for acceleration based on general relativity, all you would do is add this term to your Newtonian r double dot acceleration term, and you would get something that is accurate on the scale of 1 over c to the fourth, which is very accurate because, as we know, c, the speed of light, very, very large number. The main formula that I'll be focusing on though in this lecture is this perihelion precession formula. So what does that mean? So this delta theta over here is the angle that perihelion shifts per orbit. So in general relativity, when you were solving a two-body problem, the perihelion will precess and it'll precess by this angle per orbit. And I think that's really just best illustrated by this image over here. You can see on top we have Newtonian gravity. This planet is orbiting, or let's just call this a planet and a star. This planet is orbiting this star in a very well-behaved orbit. And a thing to note is that the space on this floor, this blue grid, is not bent in any kind of shape. It is flat, just as Newton originally thought. Now, for the general relativity case, we can see that this space is warped. It is warped right under this massive object, just as Einstein predicted. And this planet that is orbiting it is precessing. And if you notice that precession is based around the perihelion of this orbit, or which is, the point in the orbit at which it is closest to the star. So very cool in that case, and I just think this is a good visualization. So we will be applying this formula shortly. So just keep that in mind. Where will we be applying it? Well, we'll be applying it to Mercury's orbit. So when we observe Mercury's orbit, we observe the same phenomenon as can be seen again on the right here with another visualization, this one by Dr. Fitzgerald, where relativity effects are extremely exaggerated, but you can see that same kind of precession motion going on. So why Mercury? Well, it is the closest planet to the sun. So because of that, it has the most extreme relativistic effects due to the fact that it is just very close to the super, super massive object. Also, because it is the closest orbit, it is the fastest orbit. So it is the planet that is traveling the fastest in our solar system. You can see it has a very fast orbital period of 88 days here. Um, it has a very eccentric orbit, the most eccentric orbit in the solar system by zero point 0.2, which is uh, very high, and then a very small semi-major axis as well. As you know, Earth is 1 AU, so this being 0.38 AUs just shows you how close it really is to the sun. So, um, astronomers in the 19th century found this precession um, and tried to explain it using Newtonian gravity via uh, effects from other planets pulling on it because perturbations can happen just from gravity from other planets. But they found a discrepancy of about 43 arc seconds per century that they just did not have an explanation for and they could not account for. So this anomaly here became a critical observation and a test case for any new gravitational theories that would come out. So conveniently, not that long after, we did have a new gravitational theory to come out. So this table here is just breaking down the effects on the perturbation of Mercury's orbit in this perihelion shift. So this is breaking down the Newtonian contributions. So as you can see, in this table on the right, Venus, the closest planet to Mercury, pulls on it quite heavily. So does Earth and Jupiter. As always, Jupiter is always going to make an appearance there. But just from the planets alone, we get this 532 arcsecond per century shift, and the total is 573 so it's quite a bit off. Um, so in 1915, when Einstein published his theory of general relativity, they derived the formula for perihelion precession that we saw a few slides ago, and they applied it to Mercury's orbit. So when they applied this formula, and this is an important thing to note is that this formula actually is for one orbit around. So you had to apply that for a century because that is how they measured these orbits. So you take that 88 days and you divide it into 100 years and you solve out for it. But you will get that you get this 43 arcsecond per century term, which is fantastic. It verified. It was the first successful verification of Einstein's theory of general relativity, which is one of the most famous theories of all time. So, very cool that orbital mechanics played a role there. Something that I like so much. But as you can see in this table, it is highlighted in green. It is 43 arc seconds per century. So, it still has less of an effect than the Earth and uh, Jupiter and Venus. So, smaller effect than other planets pulling on it. So, even in an extreme case like Mercury, where you're super close to the sun and you're traveling at such a high speed, it's still uh, not as big of an effect as, like, say, a third body gravitational force or anything like that. So, very cool. Um, so this was, like I said, this was the first uh, successful test of relativity. And just a small side note is that further uh, experimental validation was needed before everybody was really convinced on this. And that extra validation came 4 years later in 1919 when a famous astronomer named Eddington did his experiment where during a solar eclipse, they tested how light bent around the moon and got to Earth. And once that was verified and this was verified, then people really believed that relativity was indeed the real deal and that it could be used to, in measurable systems. So very cool. Really redefined how the physics world thought about space and time and gravity. So, uh, where this table came from and what we talked about briefly in class is this paper Parker uh, Park et al. From 2017. It's in the Unit 3 files, I believe, on the course website, and it's linked at the end of this PowerPoint. But so the Messenger mission, which is an acronym. The M is for Mercury. I'm not sure what the rest is for, but it went around Mercury's orbit for 4 years, taking very, very precise measurements of the orbit and allowed us to recreate its orbit in very accurate simulations. And what these researchers at JPL in this paper were able to do using these super precise measurements was test Einstein's theory to extreme precision, as precise as we could get nowadays, and they confirmed that indeed his formulas hold up to a very extremely high order of accuracy, and that there is nothing more that we are missing, so there's no unknown body that's unaccounted for, and there's no new theory of physics that needs to be explained to find Mercury's motion. It is all accounted for, which is very cool that we were able to do that and that we could calculate the orbit of this planet to such high precision. So, to expand on that, there's still more work being done, which this is the Bepi Colombo, I believe is the name of it, is the name of another probe that is being sent to Mercury right now by the European Space Agency to do more tests to further verify these results and just to have something else up there orbiting Mercury taking more data. Very cool. So, obviously, it's very significant discovery. We shifted from a Newtonian mechanics point of view to a modern gravitational theory, which really changed the way we think about space and time. And, verifying Newton's result, Einstein's theory led to many, many, many more discoveries, and there's going to lead to more discoveries to come with relativity. So, Mercury, again, remains key point for testing these kinds of things. It's very cool that we have a planet that's that close to the sun that has significantly measurable relativistic effects. Who knows where we would have been if we didn't have that test point? Uh, I'm sure it would have been different to verify the results and also to do more testing measuring relativity. So it's very cool that that's there. Um, yeah, we again sending more spacecrafts up there to make sure to map out the sun's gravitational field and to get a better understanding of even more precise measurements of relativity. Because I guess in the future we're going to want, more long-term deep space missions and also lots of things do gravity assists around the sun. So that's a really big point of focus for this. And uh, yeah, for most applications, it's not super significant, but there are a lot of applications in which it is. So it's good that we know how to account for that. So to talk about those applications, the most uh, widely used ones right now are for GPS satellites. GPS satellites orbit the Earth at 20,000 kilometers and about 4 kilometers per second. So this is this is a decently high altitude and a very fast speed. So at this altitude and speed, you can measure relativistic effects. So these relativistic effects actually kind of offset each other. So because these satellites are uh, traveling faster than an observer or a clock here on the ground, they are going to be slowed down by about 7 microseconds per day. But because they're in a higher orbit, farther than a massive object, their clocks are going to tick faster by about 45 microseconds per day. So you take this 45 that it should be ahead, you minus the 7 that would be behind, and you get that it's about a time dilation of 38 microseconds per day, or that satellites or a clock on board a satellite would be ticking 38 microseconds per day faster than a clock on the ground. And this is actually extremely important because GPS systems are extremely precise systems. They require accuracy in the order of nanoseconds. So these effects, 38 microseconds, uh, it's like 38,000 nanoseconds, pretty sure. So that is quite a lot for it to be off. So if it's not, again, oh, yeah, here you go. So if it's not corrected, the errors will accumulate at a rate of about 10 kilometers per day. So if we didn't discover relativity and we weren't correcting for relativistic effects, your GPS satellites would get off by about 10 kilometers at the end of the day. So pretty wild stuff. Um, Definitely do not want that. So what they actually do is that they design clocks that are going on board these satellites to tick slower, and then they also do mid-flight adjustments, but they tick just a smidge slower so that they could try to offset these effects as much as possible without doing mid-flight adjustments. So for other systems that aren't GPS satellites, it's usually negligible. Another reason for that is, like I said, that offsetting effect where um, you're in a slightly higher gravitational potential, so you're going to get slightly faster time, but then you have a high velocity, so you get slightly slower time. So it usually cancels out in a way where it's not important unless you're making very precise measurements. But just for normal orbital determination, it's not usually taken into account that it's not usually taken into account into an overall thing, but most orbital determination models and software nowadays will just include relativistic corrections because we have the processing power for it. So there's really no reason not to. Um, and here, just to iterate again, that yeah, very important and precise in long-term systems. So this graph kind of shows you the x-axis is going to be your orbital height. Sorry, I got my low power notification. So this x-axis shows your circular orbit height above sea level, and your y-axis is your time dilation. So you can see on our red line here, this is going to start at the negative because this has to do with your velocity. So if you're close to Earth, you're going to have a higher velocity, more time dilation. Um, And then this blue line is from the gravitational field. So it starts in the positive because your clock is going to tick slightly faster. And when you're in the gravitational field, it's not going to be like very close to Earth. It's not going to be super significant. But then as you get farther away, these geostationary and geosynchronous orbits, it is very significant. And then of course this pink line in between is the total time dilation. So that you could see this additive effect here, and you could see it actually crosses the x-axis here. So there is a point at which it cancels out. But for different satellites that they have and different systems that they have labeled here, you can see those effects. And of course, you have GPS here, which we said is 38 earlier. So there it is on the pink line. So, uh, lastly, we'll just talk about maybe some future work is interplanetary trajectories. This has been a hot topic lately, especially with talking about sending manned missions to Mars. So if you're going to travel to other planets, if you're going to want to use relativistic corrections, so using whether you're using gravity assists or not, um, it's gonna a long mission and small time dilation errors will definitely affect your trajectory in a significant way. The finite speed of light causes big time delays, which is within the theory of relativity, so I felt like it was important to include it. Um, we could see that if you have a 24-minute delay between Earth and Mars, Mars is one of our closest neighbors, and it's still 24 minutes delayed, so it's a very long time. You're not going to be able to correct your navigation uh, via control room. You're going to want to have that autonomously on board the control ship. So it's important to have relativistic corrections built into our systems. Um, we also see crewed missions that are going to be going out will depend on onboard atomic clocks. And actually, a system that NASA is putting out right now, which I think is very interesting. If you guys have the time, I would definitely look into it. It's called DSAC, and this is an interplanetary GPS network. So it's going to be an atomic clock that is shot into deep space, and crews are going to be able to access it to make sure that they're on the right time and they don't have to keep pinging back to Earth, which could take a very long time. So, just going to wrap things up now. Uh, Again, Newton, great, very great, but not as good as we can get. We relativistic effects are measurable and they are seen and they should be corrected for if needed. Um, we use Mercury to prove that Einstein's theory of general relativity is the real deal and that it can be seen within our solar system and there are relevant cases, and how these relevant cases can affect GPS satellites in a very significant way, as well as interplanetary missions and anything that is going near the sun, near any massive body, or near or have any kind of long-term viability. And then on the right here, one more time, is just again another visualization, if you needed it, of how this perihelion is shifting in this orbit as predicted by relativity, and this would not be happening if it were not accounted for. So very interesting there. Um, if you guys have any more questions, let me know. Everything I used here is linked, and I will be sharing these slides. As well as Dr. Fitzgerald helped me out a lot with this, and he has a great slide deck on relativity too, if you guys are interested. So thank you so much.